Welcome to qnawire.
We are told that an electron in a cathode ray tube accelerates uniformly from 2 times 10 to the 4 meters per second to a speed of 6 times 10 to the 6 meters per second. This occurs over a distance of 1.5 centimeters. So this occurs delta x equals 0.015 meters. It's a conversion from centimeters to meters. We would like to know in what time interval the electron travels this 1.5 centimeters. In other words, how long does it take for the electron to speed up from 2 times 10 to the 4 to 6 times 10 to the 6 meters per second, given this value of delta x? Well, we are going to assume, as it states in the problem, that the cathode ray accelerates the electron uniformly. So we can consider the kinematic equations. V final equals V initial plus acceleration times delta time, change in time. We also have V final squared minus V initial squared equals 2 times the acceleration times delta x. And we could also use delta x equals V initial times time plus 1/2 acceleration times time squared. Right. Let's try to stick to these two for now, right? Because we know V0 and Vf, just like we have in these two problems here. So what if we calculate the acceleration from the second equation? To do that, we would have the acceleration equals V final squared minus V initial squared divided by 2 times delta x. Well, we have V final, we have V initial, and we certainly have the delta x. So all we have to do is calculate what this equation is asking for. So we would have 2 times 10 to the 4 squared, 6 times 10 to the 6 squared, 6 times 10 to the 6 squared minus 2 times 10 to the 4 squared. All that is divided by 2 times 0.015. Okay, that's going to be 36 times 10 to the 12 minus 4 times 10 to the 8 divided by 0.03, right? Okay, well that's going to be equal to, let's factor out the 10 to the 8 in both instances, 36 times 10 to the 4 minus 4 divided by 0.03 all times 10 to the 8. Now we can clearly see that this 4 is really quite negligible compared to 36,000, right? Sorry, that would actually be 360,000. Right, because 10 to the 4 is 10,000. 10,000 times 36 is 360,000. So I'll just approximate this as 360,000 to 3 divided by 0.03 times 10 to the 8 still. And those units would, of course, be in meters per second squared, given that we were using meters per second and meters. So if we take 360,000 divided by 0.03, we'll get a value of 12 million. So 12 million, 123 times 10 to the 8 still, meters per second squared. So let's just rewrite that as 12 times 10 to the 8 plus 6, or 14 meters per second squared. It's a very, very, very large acceleration. Okay, we'd like to know over what time frame this occurs. So to do that, we're going to use this first equation, Vf equals V0 plus A delta t. Let's solve that for delta t. That's just going to be subtracting the V0 and dividing by the acceleration. right? So in other words, that's going to be that 36, 6 times 10 to the 6. 6 times 10 to the 6 minus the 2 times 10 to the 4 divided by 12 times 10 to the 14. So as we can see, this will be a very, very small time since we're dividing by a very large number. So we have 6 times 10 to the 6, that means 6 million, minus 20,000 divided by 12 followed by 14 zeros. Okay, and I get a value 4.98 times 10 to the minus 9. That will be in seconds. So roughly 5 nanoseconds. Okay, so that's the amount of time it takes for this electron to travel 1.5 centimeters, and its acceleration we already calculated, 12 times 10 to the 14th meters per second squared.